Good morning, everyone. This is lecture number 6 in the series on silicon and wide bandgap power devices. My name is Anant Agarwal, and I have Dr. Arash Salami with me, who has helped me prepare these slides. And once again, I would like to acknowledge the support of Office of Naval Research to prepare this lecture series. So, last time we had discussed the p-n junction, forward bias case and reverse bias case, and in reverse bias we had two types of leakage currents. One was the diffusion current, which we had called I0, and then there was a leakage current component, which is due to the thermal generation of electron hole pairs in the depleted space charge region, also called SCR. So, as we increase the reverse bias, the space charge region increases, and then the thermal generation of electron hole pair currents, which depends on the lifetime, and Ni increases because of the volume of the depletion region is increasing, and the electric field is increasing also at the boundary of the p-n junction. A point comes where the current, reverse current, increases very rapidly. In fact, it is much more rapid than is shown here, and this current is called the avalanche current, and the point at which it starts increasing is called the avalanche voltage. So, this is the result of high electric field in a reverse bias p-n junction, and essentially what is happening is that as we increase the reverse bias, you can see that the depletion region is expanding on both sides, and this is also called the space charge region, SCR, and the electric field is pointed from right to left because there are positive donor atoms here and negative acceptor ions here. A point comes where this electric field is so high at the center that the electrons that are moving from left to right against the electric field start gaining enough energy to knock off an electron from the host silicon lattice. That is, they gain enough energy to send an electron from valence band to the conduction band. In other words, they can break the covalent bond between the two neighboring silicon atoms, and then that leaves a hole behind. So, every electron that knocks and liberates an electron from the silicon lattice also creates a hole, and holes start moving to the left under the electric field. Then the newly generated electron hole pairs move in opposite direction and again gain enough energy to create electron hole pairs, and this chain reaction goes on, and that is why we have such a rapidly increasing reverse leakage current, or so called the avalanche current. So, to summarize what I said, mobile carriers are accelerated in the presence of high electric field until they gain enough energy to create electron hole pairs upon collision with the lattice atoms, and this is called impact ionization. And impact ionization is described by two coefficients, alpha n and alpha p, for electrons in holes, and they are defined as the number of electron hole pairs created by a mobile carrier traversing 1 centimeter through the depletion region along the direction of the electric field. So, if an electron travels 1 centimeter under the high field, it will create alpha n number of electron hole pairs, and same thing for holes. And it's easy to understand why alpha n and alpha p would be strong functions of the electric field, because the higher the electric field, the higher energy they gain, and they can create more electron hole pairs as they traverse the high field depleted region of the p-n junction. So, a multiplication coefficient is defined as the total number of electron hole pairs created as a result of generation of single electron hole pair at a distance x from the junction. So, and that is given by this expression where alpha n and alpha p are functions of electric field in the junction, and remember the electric field inside the junction is also function of x. So, alpha n and alpha p become functions of x, and as so again the multiplication factor is the total number of electron hole pairs created as a result of a generation of single electron hole pair. That means a single electron hole pair is created and the electrons and holes accelerate in opposite directions, and they create more electron and hole pairs as they collide with silicon atoms. So, m simply represents the total number of electron hole pairs created by one electron hole pair. So, naturally mx goes to infinity if the denominator this part goes to 1. So, this is the definition of avalanche breakdown, and this is the integral we have to do assuming we know alpha values as a function of electric field for a given material. And this is the way most numerical calculations calculate the avalanche, because they have a table of alpha n and alpha p as a function of electric field, and since for a given geometry and a given reverse bias we know what is the electric field at any point x, we can calculate this integral and equate it to 1, and the voltage at which this integral goes to 1 is where the avalanche breakdown happens. Now, if we are doing hand calculations and one-dimensional calculations, it is not possible to do that integration by hand. So, we have defined another way of roughly determining the breakdown voltage by assigning a critical field for a given semiconductor, and that is called EC. And when the maximum field in the reverse bias junction at this junction reaches the critical breakdown field EC, then we say that this semiconductor is breaking down due to avalanche. So, please understand this is a oversimplification of the real avalanche breakdown, but this allows us to estimate the breakdown voltages of various junctions of different dopings and thicknesses. So, here we show a one-sided p-n junction, high p doping and low n doping, and when we apply a reverse voltage VBR, we deplete more on the n side, less on the p side. Electric field is maximum at the center or at the junction and then the electric field goes to 0 on both sides. We can neglect the depletion width on the p side because p doping is so high that this would be negligible, and we can simply work with electric field on the n side, which has a maximum value at the interface of the p and n junction and goes to 0 at a distance w. Now, the area under this is the voltage applied to the junction, and in this case it will be the built-in voltage plus the externally applied voltage VBR. And from Gauss's law, we have seen that VBI plus VBR would be given by this equation. So, if we define a critical electric field for a given semiconductor, then we can do this calculation, and in most cases we are very close to the avalanche breakdown voltage calculated by the impact ionization factors alpha n and alpha p. All right. So, with that, let us move on to comparison of different semiconductor properties. As we had mentioned earlier, we will consider 3 semiconductors: silicon, 4H silicon carbide, which is a particular polytype of silicon carbide, as called hexagonal lattice, and gallium nitride. Energy band gaps are increasing. There is a substantial difference between silicon and silicon carbide, 1.11 to 3.26, almost factor of 3, and then there is a small incremental difference between silicon carbide and gallium nitride. Now, this band gap is higher because the bonding between the host lattice is much stronger in silicon carbide and gallium nitride, which essentially means that the breakdown electric field EC that we defined in the previous slide is also high. So, generally electric field is a function of doping on the lightly doped junction side. So, in this case we have quoted the numbers for doping of the n side being 10 to the 15, which is fairly low doping. And we will find that as we increase the doping, actually the critical electric field goes up. So, for silicon it is about 0.28 megavolts per centimeter. For silicon carbide it is about 7 times higher, 6 to 7 times higher, about 1.87 megavolt per centimeter, and for gallium nitride it is about 2.35 megavolt per centimeter. And remember, these numbers only correspond to this doping. As we increase the doping, the critical field values will go up. Dielectric constants are about the same, and effective density of states NC and NV are given here for reference. So, as we had pointed out that the intrinsic carrier concentration is a function of band gap. So, higher the band gap, lower is the intrinsic carrier concentration, and that means we can operate these devices at higher temperature because Ni increases with temperature, but since Ni is so low to begin with for silicon carbide and gallium nitride that it can take very high temperatures to make Ni equals to the background doping. So, it will not easily become intrinsic. So, here are some equations from Professor Baliga's book. You can see the reference below. So, again Ni is given by this expression effective density of states, and e to the power minus E g over 2 k T. Higher the band gap, lower is the Ni, and higher is the temperature, higher is the Ni. So, these are good expressions to have in our tool set, because we will use them to calculate Ni for different semiconductors at different temperatures. And here are the Ni values at room temperature 300 K. You can see silicon is about 10 to the 10, silicon carbide is about 10 to the minus 10. So, that per centimeter cube, that means 20 orders of magnitude lower for silicon carbide and almost 21 orders of magnitude smaller for gallium nitride. So, what does that mean? If you remember, the leakage currents were proportional to Ni over the lifetime, and if Ni is so small for wide band gap semiconductors, then the leakage current is going to be very, very small. So, that is what we find in practice, and that is why we think these are good semiconductors for higher temperature operation. Now, let us talk about doping these semiconductors. So, let us talk about N-type semiconductor doping, that is donors. So, for silicon we usually use antimony, phosphorus and arsenic, and the energy levels for these dopants are shown here. These are measured from the conduction band. So, for example, phosphorus would be 46 milli electron volts below the conduction band edge. So, if this is the conduction band edge, this would be 46 milli electron volts below. And then for silicon carbide, we have two donors, phosphorus and nitrogen, which are roughly 61 milli electron volts. So, fairly shallow. In gallium nitride is doped with silicon to make it N-type, and that is very shallow, 30 milli electron volts. For acceptor or P-type semiconductor, we have boron, aluminum and indium. Indium is very, very deep and not very effective for silicon. So, mostly we use boron, which is 44 milli electron volts above the valence band edge. And now, for silicon carbide, the problem is that both aluminum and boron are fairly deep, in the sense that aluminum is 200 millivolts above the valence band edge, and boron is even higher. And same problem in gallium nitride. The magnesium is a P-type dopant, also an acceptor, which is fairly deep. So, the problem is these deep energy levels, such as aluminum and silicon carbide or magnesium and gallium nitride, do not ionize 100% at room temperature. So, if you remember this slide from the previous lectures, you see that we had donor atoms for N-type silicon, and these donors were able to give up their electron to the conduction band, because this energy was very, very small, and we practically at room temperature all the donor atoms were ionized, meaning they had given up their electrons to the conduction band, and therefore, we could write N equals to Nd. And same thing for acceptors. If this acceptor level is very, very close to the valence band edge, then an electron can easily jump from the valence band into the acceptor level, leaving a hole behind, and therefore, we are able to write P equals to the density of acceptors in A, and we can do the simple calculation. Electron concentration is Ni squared over P, and P is equal to Na. Now, if we move this donor atom below, or we move this acceptor level above the valence band edge, then it is much harder for these donor and acceptor ions to ionize, and at room temperature we will find that they are not 100% ionized. So, here is the calculation given from Professor Baliga's book cited below. What we are plotting is the number of donor atoms ionized divided by the total number of donor atoms as a function of temperature. So, obviously, as we raise the temperature, it becomes easier to ionize the donor atoms, because electrons can gain enough energy to overcome the higher donor or acceptor level. So, we have plotted this fraction of Nd plus over Nd as a function of doping Nd. So, for 10 to the 16 doping in silicon carbide, for example, this is doped with donor nitrogen. Then you can see as we raise the temperature, we can get more and more ionization. At room temperature, you can see it's almost 96-97% ionized, because silicon carbide has nitrogen level which is only 61 milli-electron volts below the conduction band edge. But if we dope it higher, you can see at room temperature it's only 87% ionized, but as we increase the temperature, it can become almost 94% ionized. So, as we increase the doping, the ionization reduces. For 10 to the 18 doping, you can see we only have slightly more than 50% donors that are ionized. So, basically, if your donors are deep, as in silicon carbide, then you don't get all the electrons from the donors at room temperature and even at higher temperature. Similar calculation has been done for aluminum as an acceptor in silicon carbide, and you can see even for very lightly doped material like 10 to the 14, we only are 85% ionized at room temperature. 10 to the 15, we are about 50% ionized. 10 to the 16, only about 20% ionized. And for higher and higher doping, we are less and less ionized, but again ionization increases as a function of temperature. So, this is a consequence of very deep energy levels, and this is a problem we have to consider when we design power devices. So, we will come back to this. Now, let us consider the electron and hole mobility. So, this is the electron mobility plotted a function of doping concentration, and remember that as we increase the doping concentration, the mobility reduces because of the impurity scattering, and you can see silicon is pretty high at low doping values, almost 1400 centimeters square per volt second, and then comes silicon carbide, and then comes gallium nitride. But for high dopings, you can see gallium nitride stands out and maintains the high mobility. So these are calculated and measured, combination of calculated and measured values. Again, the data has been taken from the book by Professor Baliga cited below. And same thing for holes. We can see the hole has always a higher effective mass than electrons in silicon, gallium nitride, and 4H silicon carbide. So the hole mobility is always less than the electron mobility. So in silicon, it's fairly respectable, about 1/3 of electron mobility, about 500 centimeters square per volt second, which rapidly reduces due to the impurity scattering as we increase the doping density. But in gallium nitride and silicon carbide, the whole effective mass is much higher. So the mobility also is very, very low at even the low doping concentrations. Then we had also discussed that mobility is a function of temperature, and that's due to the phonon scattering. If we increase the temperature above the room temperature, generally the lattice scattering of phonon scattering dominates, and as we had discussed, the mobility of electrons and holes reduces. So here we have shown you the behavior of electron mobility for a doping n-type doping case of 10 to the 15 or less, and you can see that the electron mobility reduces for all three semiconductors, and the same thing for holes. Due to the phonon scattering, the mobility is reducing with temperature. So now we see that the mobility for electrons and holes is a function of impurities and function of temperature, and there is a complex relationship between phonon scattering and impurity scattering. So we put all this together from these equations from Professor Baliga's book, where N represents the total number of acceptors and donors in a given semiconductor. Remember, the scattering takes place with not just acceptors or not just donors, it's the sum of donors and acceptors. So we have given you these simple equations which are approximate, where mobility of silicon is described as a function of doping and temperature, and the same thing for silicon carbide and gallium nitride. It's good to have these equations because we will use them to calculate mobilities at different temperatures and dopings, and the similar expressions for holes. And again, you can see we consider the total dopants, and since the lattice scattering dominates at higher temperature, we see temperature dependence, which is almost exponentially dependent on temperature to the power different powers, but almost similar to what we see in different semiconductors. So coming back to the critical electric field, as I had alluded earlier, the critical electric field for silicon carbide and gallium nitride is much higher than silicon because of the higher band gap, and you can see mobility for low doping case like 10 to the 15. We see that mobility for silicon carbide is sorry, not mobility, the critical breakdown field for silicon carbide is almost slightly below 2 megavolt per centimeter. So that's quite higher than silicon, which is 0.2 megavolt per centimeter. But now I had mentioned that as we increase the doping, the critical electric field increases, and we have shown the same case for silicon carbide, gallium nitride, and silicon. As we increase the doping concentration, the breakdown field increases, and for something like 10 to the 16 doping, which is very normal for 1200 volt type devices in silicon carbide, you can see the breakdown field is almost 2.2 megavolt per centimeter, where silicon is about 0.4 megavolt per centimeter. So, almost factor of 5 higher for silicon carbide, and of course, gallium nitride is also slightly higher than silicon carbide. So, again we have given these expressions to you from Prosobolic's book, critical field for different semiconductors as a function of doping are provided here. So, with that, let me stop here today's lecture, and next time we will talk more about the power diodes, and we will start with PIN diodes, which are very common in silicon industry. Thank you very much.